The relentless march of time and environmental forces inevitably degrades our built environment. Cracks propagate, corrosion advances, and structural integrity diminishes, demanding constant, costly human intervention. This cycle of decay and repair represents a significant drain on resources and a persistent vulnerability. We stand at the precipice of a new epoch in material science, an era where our structures are not merely static constructs, but dynamic, living entities capable of autonomous self-repair. This is the promise of self-healing materials. Self-healing materials possess an inherent ability to restore their original properties after sustaining damage. This revolutionary capability fundamentally redefines durability and longevity in engineering applications. It shifts the paradigm from reactive maintenance to proactive intrinsic regeneration. The core mechanisms often involve the controlled release and reaction of healing agents. These agents are typically embedded within the material matrix, poised for activation upon damage. The precision of their deployment is critical for effective restoration. Polymers represent a fertile ground for self-healing innovation. Intrinsic healing mechanisms leverage the inherent mobility of polymer chains, allowing them to re-entangle and bond across a fracture plane. This process often requires external stimuli, like heat or light, to initiate. Extrinsic healing, conversely, involves the incorporation of healing agents. These agents are typically encapsulated within microcapsules or distributed through vascular networks. Upon crack formation, the capsules rupture, releasing the healing agent into the damaged area. The released agent then reacts, often with a catalyst embedded in the matrix, to polymerize and fill the void. This targeted repair mechanism effectively seals microcracks before they can propagate into catastrophic failures. The efficiency of this process is paramount for structural integrity. Microcapsule-based systems are a leading approach in self-healing concrete and composites. These microscopic spheres, typically ranging from tens to hundreds of micrometers, contain a liquid healing agent. They are designed to be robust enough to withstand mixing, but fragile enough to rupture under stress. When a crack forms, it propagates through the material, inevitably intersecting and rupturing the embedded microcapsules. The released healing agent then flows into the crack, initiating a polymerization reaction. This seals the damage, preventing further ingress of corrosive elements. The selection of the healing agent and catalyst is critical for optimal performance. Factors such as viscosity, reaction time, and compatibility with the host material must be meticulously engineered. This ensures a robust and lasting repair. Beyond discrete capsules, advanced designs incorporate vascular networks within materials. These intricate channels mimic biological circulatory systems, continuously supplying healing agents to potential damage sites. This allows for multiple healing events over the material's lifespan. Integrating these materials with smart infrastructure concepts elevates their potential. Embedded sensors can detect microcracks or stress concentrations in real time. This data can then trigger the release of healing agents or even guide autonomous repair robots. Predictive analytics, powered by artificial intelligence, can anticipate material fatigue and initiate preventative healing. This creates a truly sentient infrastructure, capable of self-diagnosis and self-remediation. The future of construction is inherently intelligent and adaptive. The implications of self-healing materials are profound for civil engineering. They promise significantly extended service life for bridges, roads, and buildings, drastically reducing maintenance costs and resource consumption. This contributes directly to a more sustainable future. Imagine structures that autonomously repair earthquake damage or corrosion from harsh environments. This resilience enhances safety and operational continuity, particularly in critical infrastructure. The need for human intervention becomes minimal, reserved for major overhauls. This technology represents a fundamental shift in our relationship with the built environment. From static constructs, we move towards dynamic, regenerative systems. The autonomous metropolis, constantly mending itself, is no longer a distant dream, but an engineering imperative.